They only really like chocolate, vanilla, and strawberry ice cream, but in a cone, you can arrange those flavors in different orders for a completely new taste experience, right? Because in a cone, you got to eat from the top down. You start eating on the bottom, it flops, it's on the sidewalk, and you're holding a cone and pouting. Okay? So you got to go top down. So those different orders make different cones. Okay? Just work with me. So what we want to know is, how many different 3-scoop cones can be made from those 3 flavors if you do not double up on a flavor? So take a minute, list them out. How many different, like for example, chocolate, strawberry, vanilla, that's different than vanilla, chocolate, strawberry, or whatever. So list them out on your paper, how many different 3-scoop ice cream cones we can make if we just keep rearranging them. We got them all listed? How many did you come up with? 6. Okay? So list them all for me. Give me one. Vanilla, chocolate, strawberry. Then? Vanilla, strawberry, chocolate. Then? Strawberry, chocolate, vanilla. Chocolate, vanilla, strawberry. Chocolate, strawberry, vanilla. Strawberry, vanilla, chocolate. So there are the 6 possible ways. And yes, you can argue whether you think that's different or not, but they are different. I am an ice cream connoisseur. I will tell you that's very different. Okay? So now the question is, what we want to get to is we want to not have to list all these out. Okay? Because when we get to the next problem, we start talking about we have more flavors than just 3 flavors. Now we have, it says here, you on the other hand are more adventurous with your ice cream. Baskin-Robbins Ice Cream Shop offers 31 flavors for your enjoyment. You are open to all of them. How many different 3-scoop cones can be made? Well, now if I start with 31 flavors, that's a whole lot of possible ice cream cones, isn't it? And so we have to come up with a way of calculating this so we don't have to list them all out. It's not feasible for us to do it in every problem. And so how can I calculate this out without listing them all out? And what it does is it comes back to something in probability that we call as the multiplication counting principle. An example of that would be, let's say, we're going to take a side note here for a second. Let's say I've got these people running for president of student council. Let's say we got Albert, Allie, Aaron, Andrea, and they're running for president. And then these people running for vice president. Let's go Bill, Beth, Bryn, Bob, Riel. There we go. How many possible combinations are there? Why 20, Tyler? Because you're right, there is. I'm not arguing with that. How did you get 20? Multiply 4 times 5. Now, again, we're back to this. Why does that work? Because if I think about it, think about all the possible combinations. We could list out 20. It wouldn't be that hard. But I could have Albert as president, Bill as vice president. Albert as president, Beth as vice president. Albert as president, Bryn as vice president. Albert as president, Bob. Albert, Riel. Okay, there's 5 coming out of Albert. And then if I go to the next one, I could say Allie and Bill, Allie and Beth, Allie and Bryn. It's going to get to be messy, isn't it? But from each of these 4 people, how many lines are going to come out from each one? 5. So 4 people, each with 5 lines. 4 times 5 is 20. That is what we call the multiplication counting principle in terms of probability. And so we can use that same idea in this problem. And me with my wonderful artistic ability is going to say, well, let's make this cone here. Here's my cone. My 3-scoop cone. Okay? How many choices do I have for the top scoop?
31.
No, just 3 right now. We're not doing the second one yet. Just 3. Okay? We're just doing chocolate, strawberry, vanilla first. Now, once you pick a flavor, chocolate, vanilla, strawberry, doesn't matter. You're not going to double up on it. So now I'm down to 2 choices, and now I'm down to 1 choice. So I could do 3 times 2 times 1, or that's also 3 factorial. Remember factorial? Okay, which is 6 different 3-scoop cones. Yay or nay? Okay, we can use the same idea for the second one. If we have 31 flavors and we need a 3-scoop cone, here's my 3 scoops. How many choices do I have for the top one? 31. Now I can't double up, so I'm down to 30 and then 29. And so this would be 31 times 30 times 29, which gives me how much? A lot. Be more specific. 26,970 different 3-scoop ice cream cones. Oh, think of the possibilities.
Or you could just get one of everything.
Oh, you could pull out Scooby-Doo and get 1 31-scoop cone, right? Have it stacked up high.
I did it differently.
Stop. Don't take my thunder. Okay. Now,
74.
just out of curiosity, you could have 1 cone a day for how many years before?
74.
74 years before you're actually going to die? No. Have diabetes. Double up on a cone.
No, your arteries will get clogged.
Yeah, just an ice cream cone is not going to do that to you.
Yeah, it is.
After
No,
they
it's
add-
not.
If they add up for 74 years.
You can't tell me that 1 ice cream cone a day is going to kill you.
Yeah.
Now, hold on.
3 scoops.
Now, whoa. Think about it. It's about the sum of everything. It's not just if you have an ice cream cone a day, it's whether or not you have an ice cream cone on top of a hamburger, cheeseburger, and fries on top of sitting on the couch watching TV for 8 hours a day. That will do it, yes.
That's so cool.
That's me right there.
But if you have an ice cream cone and you eat healthy the rest of the day, it's not a big deal.
Yeah, but if you get ice cream going
If you eat healthy, or
You might get lack.
for example,
He said 64.
people that exercise a lot can burn a lot of calories, can't they? I don't remember the exact number, but I remember when Michael Phelps was in the last Olympics or something like that, they were talking he ate like 10,000 calories a day because he was swimming that much. He needed that much energy. That's
We
insane.
burn 1,200 calories in an hour, I think.
Yeah, it's crazy. So anyway, give me that. I like ice cream. Don't ruin my.
Do we ice cream every day?
Not every day, no. During track season, it's every Friday. I go to Dairy Queen.
Oh, yeah. She works there.
Big ice cream
It
every day.
irritates you?
Why don't you buy ice cream for everyone then?
What's
I'm
your
not
favorite
coming to you
food?
anymore. All right, so
What you get there most often?
now what this is an example of permutations. Okay, remember permutations? So permutations. If I talk about what are permutations, permutations are where you are selecting objects from a group. Where order matters. So what do I mean by order matters? That if I can take chocolate, strawberry, vanilla, and flip it around to chocolate, vanilla, strawberry, and that's something different, that is where order matters. You got that ice cream cone again, you get those nice waffle cones. Best place is down in St. Paul called Grand Old Creamery.
Oh, yeah.
Homemade waffle cones, and oh, they're great. Anyway, but the order makes a difference, okay, and that would be a permutation. The notation we're going to use for that is NPR. All right? Now, N is always the total number in the group. R is the smaller group you are selecting, or it might not be smaller, it might be the same size. Okay, yes, told you it's review. Okay, so from a standpoint of the 2 problems we were just doing, that first problem here, we had 3 flavors, we were doing a 3-scoop cone, so this would be 3P3, and how do we calculate it? We went 3 times 2 times 1, or 3 factorial, and got 6, correct? Okay. The second problem was 31P3, 3, because there's 31 total flavors. We were picking a group of 3. How did we do that? We took 31 times 30 times 29. So if we wanted to come up with a formula for permutations, NPR is n times, well, what's 1 less than n? N minus 1 times, what's 1 less than that? N minus 2. And we're going to do that how many times? Well, 31P3 we did it 3 times because there's 3 spots that we were picking in terms of the cone, right? And so R, number of times right here. Now, we don't like that as math people. Why? Because we don't know where to stop.
Can't use that one.
And so this dot, 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 we say it's R times, but it's kind of ambiguous. And there's a couple other ways we can write that same problem. Number one is, notice how we stopped at 29 here. 29 is 1 higher than 31 minus 3. 31 minus 3 is 28. 29 is 1 higher. That's another way of doing that particular thing. I can write it out as n times n minus 1 times n minus 2. I can put the dot, dot, dot in the middle and stop at n minus r plus 1. 1 more than n minus r. So you could do that. I don't like that either. The other thing is the idea of factorial. Factorial is multiplying all the way down until you get to 1, right? Consecutive integers keep going down. So 10 factorial is 10 times 9 times 8 times 7 all the way down to 1. Well, we're multiplying by consecutive integers here, 31 times 30 times 29, but we're getting rid of a whole bunch of them, aren't we? So we could think of this as 31 factorial over something. Well, 31 factorial is 31 times 30 times 29 times 28 all the way down. Well, we need to get rid of 28 all the way down, don't we? So if I divide it off by 28, 28 all the way down, then those would all divide out. So if I divide by 28 factorial, all I'm left with is 31, 30, and 29. Agreed? Now where does 28 come from? 31 minus 3. Okay? So NPR, another way of writing that is n factorial over n minus r factorial. Okay? Just a different way using factorials because you are multiplying, Tyler, consecutive integers, right? And we just want to get rid of some, and so that's just a different way of doing it. Now, of course, if you remember from way back to December, we could also do that on our calculator. There is an NPR button on our calculator. So if I wanted to do 31P3, like I had in my warm-up here, 31P3, I would go 31. It depends on what calculator you have. On this one, I have to go to Option and then go over to my probability menu. And there's my NPR button. 31P3 will tell me it's 26,970. If you have a TI, hit 31. Go to the Math menu. And then go over to the probability menu and you'll find it. Okay, find it for me right now would be good. Somewhere on a calculator you have. If you don't,
26,970.
good. You found the button. Life is good. And so you can find that, and we don't have to use it, but there are times where we have to use that factorial definition. Now that's when order matters. Now we also have situations where order doesn't matter. Okay, this time you go to an ice cream shop. It only has bowls of ice cream. It does not have cones. Okay, no cones, bowls. Now your friend still only will eat chocolate, strawberry, and vanilla. However, in a bowl of ice cream, does the order of the flavors matter? No, because if I wanted to, I could just turn the bowl and I got the flavors situated differently again, don't I? That's all, and I could take a scoop out of any flavor I want at any time. Complete ice cream freedom. Yes. I thought about this way too much. So order doesn't matter. So if you have 3 flavors and you know you're going to put 3 flavors in the bowl, how many bowls of ice cream can you make? 1. Only 1. Because those 3 flavors, it doesn't matter the order, it's just 1 bowl of ice cream with those 3 flavors. Chocolate, strawberry, vanilla, done. You can't rearrange them because it's in a bowl. It's not like a cone where you have the different orders as you kind of stack them up on top. So order doesn't matter here. Now how can we talk about that in terms of, well, we still want to expand your taste buds horizon, so we go to a shop, it's got 31 flavors, just like Baskin Robbins. How many 3-scoop bowls can you make from these 31 flavors? All right, well, if order mattered, we said there was 26,970 up here. Okay? It's got to be less, correct? Because once you pick 3 flavors, maybe it's mint, banana, and pistachio, I don't know, cookie dough, pick whatever it is. I'm just throwing 3 flavors out there. Once you pick those 3 flavors, that's just 1 bowl of ice cream. but it used to be 6 cones, didn't it? So it means there's 6 cones when you pick 3 flavors, but there's only 1 bowl. So how can I use that idea to help me figure this problem out? If there was 26,973 scoop cones,
Three.
and there's 6 cones for every bowl,
1/60.
somebody just said it,
Might have been.
divide by 6. Because every time you have 6 cones, it's only 1 bowl. So if I have this many cones, I can divide by 6.
Four-
And how many is that?
4,400.
4,485.
No,
Three-
95.
95? 95 bowls. 3 scoops. From those 31 flavors. Okay? Now, that actually you probably could do one every day for a while and you actually have a chance of getting it in your lifetime. Maybe. I don't know.
So you send that one,
Not
it's
those
not
that many
possible.
bowls a day?
How much money would that?
I don't know. You can figure that out on your own. Now, this is an example of something different when order doesn't matter. And so, if permutations is where order matters, combinations would be where order doesn't matter.
Just like,
Wait, there.
So order does not matter if we are talking about combinations, where order does matter. Order matters if we're talking about permutations. Alright, so with that said, now coming up with a formula. I know there's a button right next to the other one on there. Coming up with a formula, what do we do over here to calculate the combinations with the bowls of ice cream? Well, this would be 31C3 because it's a combination, not permutation. What we did is we took the permutation one, which was 31P3, and divided by 6. Where did the 6 come from? That came from the cones, which was 3 factorial, wasn't it? Correct?
Correct.
And so it came from 3 factorial, the 3 was right there. And so it's take our NPR, whatever our permutations are. So if I have NCR, I take NPR, and I divide it by R factorial. We divided by 3 factorial because it was 31P3. Well, now that R is right there, it'd be divided by R factorial. Now, because we have a formula for NPR, is right there, we just have to divide that by R factorial. So that becomes N factorial over N minus R factorial and another R factorial is what you end up with. A formula for combinations. Again, there are times where that formula will be helpful. There are times where you just save it on your calculator and you don't have to worry about it. Yes?
Is that NCR equals?
Yep, NCR equals. That's a C. Combinations. C for combinations, P for permutations. All right, so the big thing is you have to decide does order matter or not. Okay? Order matters, we use a permutation. Order does not matter, we use a combination. So let's do some examples here. Just a couple. So for example, I got 12 horses running a race. How many ways can we place the top 3? First things first, combination or permutation. Does order matter or not?
Yeah.
Yeah, if you are placing them first, second, third, order makes a difference. So that would be a permutation. So now it would be 12P3. You can put it on your calculator or you just start at 12 and multiply the top 3. So 12 times 11 times 10, which is
1320.
1,320 different ways. Okay? Let's say I have 20 people in here. I'm going to send 4 to the Deca store. For cookies. How many ways can we do this? Combination or permutation? Combination. Does it matter what order I send you down to the next door?
No.
No. And so that would be a combination. So 20C4 in this case, 48, 45. Different ways that we could do that. And so you look ahead there and you find, does order matter? Does order not matter? I'm not going to write this one down. We'll just talk through this one. But let's say we're giving away scholarships in the math department. I have 30 people applying for scholarships. The scholarships are $1,000, $1,500, $2,000, $2,500, $3,000. So 5 scholarships, all different amounts out of 30 people. Does order matter or not?
Yes.
Absolutely. Because if you get $3,000 versus $1,000, it makes a difference, doesn't it? So that would be one where order would matter. That would be a permutation. What if I said, hey, 30 people, 5 scholarships, they're all $1,000?
That one.
Then order doesn't matter, right? Because they're all getting $1,000 regardless. So then the order we pick them in doesn't matter. That would be a combination. We talked about the lottery the other day. Let's talk about the lottery. So lottery, there's 6 numbers. We're going to simplify it just a little bit. Because the Powerball is a little bit different than this. But we'll simplify it just a little bit. 6 numbers, and I don't remember the exact group they come from, but they all come from that bin of ping pong balls, and I think it's like 1 through 56 or something like that. And you got to match them all. Now, you probably don't know this, but does order matter or not?
No.
It does not. Because every time you ask for a lottery ticket, they put it in numerical order. It's just, there is no order, it's just the group of numbers is all you need. All right, so what's your problem, or how many different tickets can they sell? Or how many different number patterns can they do, groups? You need 6 numbers to match out of 56. So how many different possible 6 number groups are there out of that 56? Does order matter? We said no, so that'd be combinations. So 56C6. Type that in, what do we got? 32 million?
32,468,400.
So it's a chance.
So there's 32,468,436 possible number combinations for the lottery. So what's your probability of winning then? 1 out of 32,468,436.
It's a chance.
And, well, yeah, so you're saying there's a chance. It's actually worse than that for the Powerball because they go 5 numbers and then they got the separate Powerball bin. That actually decreases your odds a little bit.
The numbers
Closer to 1 in 50 million. I don't remember the exact number.
numbers can be.
Because again, you got to match the first 5, but then that last one, then they start fresh with a whole new bin of Powerballs. And I don't remember if I can't remember all the details. I should have looked them up. But at least you kind of get that idea. So we have a worksheet today, combinations and permutations.
I was at my friend's house one time, and my mom